Dynamic VAR Compensation, Static VAR Compensators. Good morning, everyone. Today, we are diving into a critical topic for modern power systems, dynamic VAR compensation. Specifically, we'll explore static VAR compensators, or SVCs, and how this technology is fundamentally changing the landscape of power factor correction and grid stability. As electrical infrastructure becomes more complex and loads become more variable, dynamic compensation is no longer a luxury, but an imperative for operational efficiency and reliability. The Power Factor Imperative, section title. Before we discuss the solutions, let's establish the problem. Why is power factor so important? In essence, it is the fundamental measure of electrical efficiency. A low power factor burdens the grid, causing excessive heating, voltage drops, and ultimately, wasted energy. Understanding and correcting it is paramount to maintaining a healthy, modern electric grid. Defining power. Definitions. Power flow in an AC system is composed of two primary elements. First, we have real power, or kilowatts, kW. This is the power that actually does the work. It runs the motor, heats the water, or lights the room. Second, we have reactive power, or kVAR. This power is essential for magnetizing components like motors and transformers, but it does no useful work. Crucially, kVAR flows back and forth between the source and the load, consuming valuable capacity and causing line losses along the way. Our goal is to minimize this reactive burden. Traditional limitations. For decades, the standard approach was using switched capacitor banks. While effective for stable, predictable industrial environments, they have serious limitations for dynamic loads. Their response is slow, taking multiple seconds due to mechanical switching. This slowness is inadequate for modern, rapidly changing loads. Furthermore, mechanical switching can induce voltage transients, which may damage sensitive electronic equipment. Finally, these banks use fixed step sizes, meaning they often over or undercompensate, never achieving perfect efficiency. The Static VAR Compensator, section title. The solution lies in power electronics. The Static VAR Compensator, or SVC, is a key piece of FACTS technology, flexible AC transmission systems. SVCs leverage solid-state components, specifically thyristors, to achieve continuous, high-speed reactive power control. This dynamic capability is what differentiates it from its traditional predecessors. SVC architecture. SVC components. An SVC comprises three major parts. First, the control system monitors voltage and power factor in real time, calculating the exact VAR requirement in milliseconds. Second, the thyristor-controlled reactor, TCR, acts as the inductive element, absorbing reactive power. And third, the thyristor-switched capacitor, TSC, acts as the capacitive element, injecting reactive power. The combination of the fixed TSC and the continuously variable TCR allows the SVC to provide a smooth, flexible reactive power range. The TCR mechanism. TCR deep dive. The true innovation lies in the thyristor-controlled reactor. The TCR uses two back-to-back thyristors to regulate the current through an inductor. By precisely controlling the firing angle, that is, the exact point in the AC cycle where the thyristors are switched on, the effective current and, therefore, the effective inductance can be continuously varied. This power electronic control means there is no mechanical movement, enabling smooth, continuous, and instantaneous reactive power absorption. Performance metrics, speed. When we talk about performance, speed is the differentiator. SVCs operate in the subcycle time frame, typically achieving full response within 10 to 20 milliseconds. This rapid injection or absorption of VARs is critical for stabilizing voltage during transient events, such as when a large steel rolling mill motor starts, or during the unpredictable operation of an electric arc furnace. This immediate response prevents system instability and voltage flicker. Industrial application, industrial use. One of the most demanding applications for SVCs is heavy industry. Consider a steel mill utilizing an electric arc furnace. These furnaces create massive, rapid, and asymmetrical load changes, causing severe voltage flicker that can disrupt the entire local grid. SVCs are deployed specifically to absorb or inject VARs in real time, effectively mitigating this flicker and ensuring operational integrity for both the mill and nearby customers. The future, STATCOM. While SVCs are robust and widely deployed, the technology continues to evolve. The next generation of dynamic compensation is the STATCOM, or Static Synchronous Compensator. STATCOMs utilize voltage source converter (VSC) technology. This gives them a significantly smaller footprint, much faster dynamic response, and the ability to maintain strong reactive support even when the system voltage is severely depressed. STATCOMs represent the cutting edge in high-performance grid stabilization. The objective, quote, "In conclusion, whether we are talking about SVCs or STATCOMs, the core mission of dynamic VAR compensation remains the same: to regulate the grid by ensuring system voltage and power factor are maintained as close to unity 1.0 as possible, even during the most challenging dynamic conditions. This is how we build a more reliable and efficient power system." Q&A. Thank you for your attention. I hope this presentation has shed light on the vital role of dynamic compensation in modern power infrastructure. I am now happy to take any questions you might have.